In this last video from our look through intermolecular forces, we're going to explore phase diagrams. Now, phase diagrams are interesting. What a phase diagram is essentially is a graph. On the one axis, we are going to have in our graph the pressure that a substance is being exerted on. On the other, we're going to have temperature. And what a phase diagram does is it basically maps out for us the phase of matter that is associated with varying conditions of pressure and temperature. Now, what's interesting and where this relates to intermolecular forces is that the zones that are associated with solid, liquid, and gas are all dependent on the intermolecular forces of the substance itself. And so let's explore this a little bit. Now, before we do, let's take a look. This is what a phase diagram looks like. And so a phase diagram tells us, okay, here's my pressure axis, here's my temperature axis. Pressure here is given in atmospheres. Temperature is given in degrees Celsius. And this is a phase diagram for carbon dioxide. What this phase diagram does is it shows that carbon dioxide is a solid in this green zone, a liquid in this blue zone, and a gas in this light pink-orange kind of zone. Now, there are some other kinds of critical ideas and points that we should uncover, and other points in this that are associated. But if we can look, as we can see, that if I just look at any given pressure and temperature condition, I can accurately determine what phase I should expect to see. So if I'm at 1 atmosphere of pressure, which is normal pressure, if I'm at 1 atmosphere of pressure and room temperature, 20 degrees, I expect carbon dioxide to be in the gas phase. And if I'm at 1 atmosphere of pressure and negative 100 degrees, I expect carbon dioxide to be in the gas phase, in the solid phase. So that's what this is really kind of going after, is this being able to give direction between the pressure of a substance and its temperature and what phase it's going to be in. Now, about some of those other kind of weird key points. So if we go back here, the triple point. The triple point is a unique point in a phase diagram where we have the interaction of all 3 phases of matter at the same time. So going back here, our triple point is at this spot right here, which the diagram tells us is negative 57 degrees Celsius and 5.1 atmospheres of pressure. At this point, at this particular set of conditions, we see all 3 phases of matter at the same time. And not only do we see all 3 phases of matter at the same time, we also see all 3 phases of matter interconverting between each other at the same time. So solid is turning into liquid, liquid is turning into gas, gas is turning into solid, gas is turning into liquid. We've got all 6 of the phase changes all occurring at the same time at equilibrium with each other at this particular temperature and pressure condition. The critical point represents a specific temperature and pressure condition where the gas and the liquid phases are no longer distinguishable from each other. And so a critical point is especially essential if we're looking at liquefying gases. So if you're going to liquefy propane, or if you're going to liquefy petroleum or some kind of gas for cryogenic reasons, for fuel reasons, whatever the case may be. The critical point is something you need to be aware of, because at temperatures and especially pressures greater than the critical point, then we start to go into this zone. And the zone that we're talking about here is this idea of the supercritical fluid. So this point here represents the critical temperature and pressure. Now, at this pressure and temperature conditions, if we go above them, that's when we get into this supercritical region. And the supercritical region is when we can no longer tell solid and gas, or excuse me, liquid and gas from one another. So we can't tell liquid and gas from one another at this point, which means, as far as liquefaction is concerned, the whole idea of condensing gases and selling liquefied petroleum gas or propane or butane or anything like that, beyond the critical point, that's impossible. You can't do it. Now, there are some interesting applications for supercritical fluids, in particular supercritical carbon dioxide. It's been used as a fluid. It's been used as a replacement or a kind of a green solution for some more nasty organic kinds of solvents. But in terms of some of the other things, the critical point is generally something that is avoided by most people in the industry. So with that in mind, how do we interpret these graphs? What kinds of questions can we be asked? Well, we can look at things like this. What is the expected phase of matter for carbon dioxide if we're at 10 atmospheres of pressure and negative 80 degrees Celsius? Well, this is where we can use our graphical analysis skills. And so if I draw a line at 10 atmospheres, and if I draw another line at negative 80 degrees Celsius, I can see that those two conditions cross in the solid region. And so the expected phase of matter there would be solid. We'd expect it to be solid at that point. Name one set of conditions where carbon dioxide can freeze or melt. Again, I go to my phase diagram. I'm looking for anything along this darker blue line. And so I just pick a set of conditions and take it from there. So I've already got a line here at 10 atmospheres. If I take that down, make a real rough estimate here, that's, let's say that's negative 55 degrees Celsius. One set of conditions that I could outline would be 10 atmospheres and negative 55 degrees Celsius. But I could technically pick anything along that solid blue line there. Why don't we see liquid carbon dioxide when we use dry ice? Well, since most of the stuff that we do is at 1 atmosphere of pressure, we can see that at 1 atmosphere of pressure, carbon dioxide does not exist in the liquid phase. It simply doesn't. Now, if we want to see liquefied carbon dioxide, we can do it, especially at room temperature conditions. We can see it at room temperature here, 20 degrees. That's somewhere in the vicinity of, let's say, about 50 atmospheres. We could see it in the liquid phase. And certainly at pressures higher than that, so long as we stay below that critical point. So the main reason we don't see it is because at our normal sets of conditions, that's not what dry ice does. That's not what carbon dioxide does. It stays as a solid when it is cold. It turns into a gas when it is warm at 1 atmosphere. There is no liquid phase in between. Now here's an example of another phase diagram. This is the phase diagram for water. And notice that water's phase diagram is considerably different. One of the things that we can notice, first and foremost, is that the gas region here is considerably smaller compared to what we saw in carbon dioxide. The solid and liquid regions are considerably larger, and in fact for water, the liquid region is abnormally large. We can also look at, here's our normal atmospheric pressure. And from that, we get a normal melting point here at 0 degrees, a normal boiling point here at 100 degrees, and gas, obviously, at temperatures above 100. Look at where our critical point is. Remember, for carbon dioxide, the critical point was at 31 degrees Celsius. For water, it's at 374 degrees Celsius. Why? What's the difference? Well, the primary difference, even though water is considerably smaller in terms of its size, in terms of its molecular weight, The hydrogen bonding in water pulls those water molecules together much, much more tightly. And as a result, we get a much larger liquid region, a much larger solid region when it's condensed. And it requires a heck of a lot more energy to turn it into a gas phase to separate those molecules from each other. So that's phase diagrams. Now, as far as practice problems, let's take a look. Give one set of conditions where water boils other than the normal boiling point. Again, we're looking at anywhere on this red line, we would see that. So if I chose a different pressure, I could use a different temperature. And so at 0.1 atmospheres, 50 degrees seems to be about where it is. 0.1 atmospheres, 50 degrees Celsius. Where can water sublime instead of melt? Well, we're going to have to go down to some lower pressure kinds of circumstances for that. But if we go down to 0.001 atmospheres, we can see that somewhere around, let's call it negative 15, negative 20 degrees Celsius, we could have that happen. So 0.001 atmospheres and negative 20 degrees Celsius. And then describe the phase transition that occurs as we go from 0.1 atmospheres to negative 100 and negative 1 to 300 at the same pressure. So we're staying at 0.1. We're going from negative 100 right here to 300 right here. And so we can see that we're going to start in the solid phase. As it goes on, we're going to transition to liquid, so the water is going to melt somewhere just below 0 degrees. That water is going to continue to warm up. Somewhere around here, it's going to boil. Again, we estimated that about 50 degrees Celsius in the previous problem. And then from 50 degrees to 300 degrees, we just get a gradually increasing temperature, getting hotter gas. So that's phase diagrams. Now, there is a lot more that we can do with phase diagrams other than these. But just to kind of get us started, we can see that there is a difference. There is a relationship between what we see in the terms of the physical properties and the temperatures and pressure conditions at which we see liquid and solid conditions for different compounds based upon the intermolecular forces. When the intermolecular forces are strong, we are going to see larger liquid and solid regions. When the intermolecular forces are weak, we're going to see weaker conditions and therefore smaller solids, smaller liquid regions, much larger gas regions as a result. So that wraps up our discussion on Chapter 6 here. If you have any questions, please feel free to reach out to me. Otherwise, I'll see you next time. Have a good day.